Welcome to this sixth lecture video for Physics 4A. In this lecture, we outline a problem-solving strategy that you will be using to solve force analysis problems for the next few weeks of this class. Moreover, this multi-step problem-solving strategy is a paradigmatic example to follow and use to fashion your own problem-solving approaches as we introduce mechanical concepts beyond the force and learn to solve more complex situations. In the first lecture video in this set, we will outline our four-step standard strategy and apply it to an inclined plane problem. And in the next video, we will apply the standard strategy to two more examples, demonstrating how this multi-step problem-solving strategy helps approach situations where intuitive problem-solving often fails. Finally, as you will find different versions of Newton's law problem-solving strategies, standard strategy just being our version at the College of Alameda, I will draw comparisons between our strategy and the one you will find in the textbook, and the one you will find in Andrew Elby's Portable TA. In this video, we will talk about Newton's law problem-solving strategy, or as you will hear me call it, the standard strategy. The standard strategy is an application of the general problem-solving approach that we talked about at the very beginning of the semester. In this context, we are applying that general approach to situations that specifically involve forces or Newton's law problems. So let me summarize the strategy that you see on screen here. So when we are tackling a force problem, we start by drawing a free body diagram or a force diagram. This is a diagram that indicates all the forces acting on the object. This is the step that generally takes the most consideration, care, and time to do it correctly. Once we have a correct free body diagram drawn, then we'll spend some time indicating certain pieces of information that will be useful in problem solving. First, we take some time considering the direction of the acceleration of the body that you are drawing free body diagram for, and that is so that we can choose a coordinate axis in which one of the axes is parallel to the acceleration. There are some special circumstances that you may consider, either where acceleration is zero, or there are particularly difficult questions where it might actually be better to have an axis pointed another way. But in general, the rest of the problem-solving steps turn out to be easiest when we choose our axis so that the x-axis is parallel to the acceleration. Once we have chosen our coordinate axis, then we do what the coordinate axes are for. It's so that we can describe the forces in terms of their components in the x and y directions. And to talk about x and y directions, you need to know what directions x and y are. Now, following through steps 1 through 3, you will be at a place where your free body diagram has a lot of information indicated graphically on the diagram. So we end the standard strategy with the final step, which is writing down the equations that we are going to solve for. Those equations come from Newton's second law. Now, I want you to notice how this doesn't really leave us with any particular solutions. We've written down an equation and that's it. And part of that is because, well, the rest is math. And perhaps less glibly, the rest of the steps depend on exactly what it is the problem is asking for. We call the standard strategy because it's the set of steps that you would go through in order to solve any problem involving forces, regardless of what the question actually asks for. So this is the strategy to get to the system of equations. And then actually solving those system of equations, it depends on what the question is asking for. So from that point on, the exact steps will vary depending on what your question asks for. Now, your textbook will give its own version of Newton's law strategy, And I will do a separate video that draws the comparison more thoroughly. In the meantime, let me just point you to where in your textbook those Newton's law strategies in the textbook can be found. A portion of them is in section 5.7. They introduce these steps as they introduce the free body diagrams. Here's the problem-solving strategy for constructing free body diagrams. These are the textbook steps for drawing free body diagrams. And because the textbook chose to split this up, the rest of the steps, you will have to find them in section 6.1, solving problems with Newton's laws. So here under problem-solving strategies, they describe the problem-solving strategy for applying Newton's laws of motion. Again, I'll do a separate video that draws this comparison more thoroughly, but this is where you can find the textbook versions of these strategies. And since in this class, we are using the Portable TA rather extensively, let me point out the parts of the Portable TA that relate to situations that deal with forces. I believe it's introduced in question 8-6. So let me get to chapter 8. Here's chapter 8, 8-6. In this problem, Andrew Elby introduces something that he calls multi-block strategy. And again, in a separate video, I'll draw more thorough comparison of our standard strategy and the Newton's law strategy that is introduced in the Portable TA. Now, back to our presentation of the standard strategy. There's a value in seeing these 4 steps laid out and having them numbered 1, 2, 3, 4. And you will see me cite those 4 steps quite a few times throughout the semester. But I think simply seeing the 4 steps spelled out isn't quite as useful as seeing the examples of seeing them applied. So let me give you 3 examples of the standard strategy application in this video. And you will see plenty more examples as we work through homework questions in other future lectures and virtual class sessions. So let me give you the description of the first example. Example 1. Block on an inclined plane. It's kind of what it sounds like. Let's say we have an inclined plane and we have a block sitting on it. And if we want to make the situation particularly simple, we can say this surface is frictionless. And because this is going to come up, let's say we know the angle of the incline. Okay, that seems like a complete description of situation as far as it goes. And for the moment, we don't know exactly what question the question is asking. But given this situation, we have enough information to start following the standard strategy. So let me work my way through the standard strategy. The first step is to draw a free body diagram. So let me draw a free body diagram of the block. I try to draw the simplest free body diagram possible. So I'm going to represent the block of mass m by a simple dot. I don't need any more detail than that. And I start thinking through what forces must be on this block. There's probably going to be a gravity on it because I think the block is on Earth, so gravity must be pulling it down. Now, as I look at the situation, I know the block is not accelerating downward straight, so that can't be the only force on the block. The block is on a surface, so I think there's going to be some contact force from the surface. One of the contact forces would be the normal force, the force that's perpendicular to the surface. So let me draw that force, normal force. And I might draw a little bit of an auxiliary figure so that I can indicate the direction of that normal force. And this dotted line would be parallel to the incline of the surface. So theta should be the same theta here. Then I ask myself again, did I draw all the forces? Usually the thing that's good to check is what's the direction of acceleration of the block. The block should be sliding, accelerating along the surface. And I look at the forces that I've drawn and try to see, can I, with these forces I've drawn, can I make the net force go in the direction of acceleration? So I look at that and see if my answer is yes. If my answer is yes, good. And I also look at what things are touching the block for the purpose of accounting for all the contact forces. So here, the only thing touching the block is the surface. So I want to account for the contact forces from the surface. Each surface is going to potentially have two contact forces, normal force and friction. Here I already accounted for normal force, and friction, the problem, I set it up to be frictionless, so I don't have to worry about friction. But if this were a question that had a friction force, then I would have to account for friction. But let me handle friction in another video. Okay, so I'm done with the step number 1. As I was saying, this is a step that takes most consideration, care, and time. Okay, let's do step number 2. Identify the direction of acceleration. We've already done that. So the only thing remaining to do is define our coordinate system. I think so. I want to make my x direction along the incline. That's going to be my x. So my y will have to be perpendicular to the incline. This way, my x direction is parallel to acceleration, and my y direction has no component of acceleration along that direction. Okay, let me draw a version of this axis that's nice and big, centered around the object. All right, step number 3 is to break down forces into their components. Now, the normal force N does not need to be decomposed. It's already along the y direction only. The gravity, on the other hand, it's got component along the y and component along the x direction. So I'll need to break it down into those components. And it's when I do this step, I also like to write down what the expressions for these components are in terms of some given quantities. Like here, I'm given theta, so I can express these legs of the right triangle in terms of the hypotenuse, mg, and the angle theta. Now, this is where I would advise caution. People who get into habit of saying, oh, x is cosine and y is sine, tend to run into problems because it won't always be the case that you can automatically associate x with cosine and y with sine. Instead, this is what I do advise. So the first is draw the triangle. I've already drawn one as I was labeling these components. Once you've drawn the triangle, then now you have to go through the geometry exercise to locate any known angle onto that triangle. So in this case, all right, I have theta here. I know this is 90 degrees. So I happen to know this is 90 degrees minus theta. I know this is 90 degrees because horizontal and vertical. So this angle here must be 90 degrees minus 90 degrees minus theta. So 90 degrees cancel out, and I end up with a theta. So this angle must be theta. Let me clean up this diagram a little bit and label that angle as theta. Okay, so this angle is theta. Doing this correctly every time will take some practice, so I recommend that you get practice whenever you get a chance. So with this angle labeled, now we can correctly figure out the magnitudes of the components using SOHCAHTOA, or in this case, SO and CA. Sine is the opposite over hypotenuse. So this opposite side of the angle theta will have the magnitude of mg sine theta. And this adjacent side is CA. Cosine is adjacent over hypotenuse. So it'll have magnitude of mg cosine theta. Notice how it's the x component that becomes associated with the sine theta in this case. And there isn't one simple rule I can give you that will always work. So the rule I am giving you is draw the triangle. Figure out the angles, always. Okay, that's step number 3. So let me now do the final step of writing down Newton's second law equations. So Newton's second law says net force is equal to mass times acceleration. And these arrows are there to remind you that these are vector equations. This single equation actually stands for two. One that says the x component of net force is equal to mass times acceleration in the x direction, and net force in the y direction is equal to mass times acceleration in the y direction. And if we were somehow working on a problem that had full 3 dimensions, then there would be g component as well. So that's what we have to write down. Let's do that. So first, net force in the x directions. I look at the free body diagram that I've drawn, and I look for the forces along the x component. My normal force has no component along x direction. My gravity has one component along the x direction. So mg sine theta is going to be equal to mass times acceleration in the x direction. Now, the way we defined our coordinate axis, the entirety of the acceleration will be in the x direction. So I can do away with the subscript and just say mass times acceleration. Okay, let's write down the second equation. Net force in the y direction. So here I have the force, normal force. The entire thing is along the y direction. Gravity has a component in the y direction, mg cosine theta. And it's in the negative y direction. And there's a couple ways you can go about it. I will give you the way I prefer. So I prefer to write down all my quantities so that all the variables like m and g are positive. And anytime I need to indicate direction, I prefer to indicate it in my equations. So here I would write down minus mg cosine theta to indicate my expectation that the y component of gravity is pointing in the minus y direction. I found this useful for those times when we get a direction of a force like a friction force that's not in the expected direction. In those cases, having one of the variables come out to be minus highlights for me that something has gone as unexpected. So with that, this is going to be equal to mass times acceleration in the y direction. Now here, the way we chose our coordinate axis will make the y component of acceleration 0. So this is equal to 0. And this is really why we choose our coordinate system the way we chose it, so that the second of our equations is a bit simpler than the other one. Because whenever an equation has everything equal to 0, there are things that cancel out. It makes life easier most of the time. So this is the end of the standard strategy. Now, I will highlight that we haven't actually solved for anything. Where the strategy has landed us in is we have a system of equations. In terms of these quantities, which may be known, may not be known. So in a situation like this, it would be very typical for something like acceleration and normal force to be unknowns, and for the question to ask us, what is the acceleration? What is the normal force? And you can see how quickly we can give that answer if someone were to ask us for acceleration. We can look at this first equation. We see that masses cancel out, and we can give this answer. Acceleration is equal to g sine theta. Or maybe the question asks us for normal force instead. Then we can see here that we can take the second equation, solve it for normal force, and quickly get normal force is equal to mg cosine theta. And because the steps for those last mile will depend on what the question actually asks for, standard strategy lands us in this stage where we are ready to answer any question that someone might ask, but we haven't quite answered it yet. Now, with this example 1, you might think, For a hypothetical question that asked for acceleration, you might say, hey, I could have given this a equals g sine theta in 5 seconds. You just look at this, g goes in this direction, you take a projection of it along the direction of acceleration, bada bing, you get a equals g sine theta. And yeah, I'm not denying that there may be questions where going through standard strategy might seem like nailing something with a power tool. For a simple, easy task, you don't need this whole framework. Let me devote examples 2 and 3 to situations where if you are trying to approach it intuitively, as in you can stare at the question for a bit and then guess the answer, if that has been the only thing in your toolbox, you would have gotten stuck. The goal of the standard strategy is to give you the steps that you can follow, even for a complicated question where no amount of staring at the question will give you easy, quick, one-step answer. We looked at this example 1, and I ended the video by noting that in this simple example, it's possible to think of an intuitive way to solve it, and that would be quicker than standard strategy. Where the standard strategy shines are the more difficult questions. So take this example of example 2, taken from question 9-5 from the Portable TA. So it asks, blocks A and B sit on top of each other. They are attached by these ropes. It says block B is heavier than block A. And it says block A is so slippery that it slides frictionlessly on block B. Okay, let me note that in the drawing. But the coefficient of kinetic friction between block B and ramp is mu. Okay, and it asks, assuming block B accelerates down the ramp after it is released, what is its acceleration? And also, what is the tension in the rope? Oh, I think they are supposed to give us the masses of the blocks. So let me label mass of the block A and mass of block B. And the drawing also shows the angle theta of the incline. Now, this is the kind of question if you are trying these one-step guesses, like acceleration is equal to g sine theta, or the tension is, I don't know, mg sine theta, and any combinations of these, m, ma, g sine theta, m, b, g sine theta, or MA plus MB. None of these are correct answers, of course, I think. So this is where intuitive approach hits its limit. The situation is more complicated. There are infinite different things that you could guess as an answer, and the chances are your guess won't be the right answer. And this is the exact scenario that is made for standard strategy. So let's work through the standard strategy. Let me start out with step 1, drawing the free body diagrams. This system has 2 blocks, so I'm going to need 2 free body diagrams, one for each object. So I'll draw one diagram for the block A and a separate diagram for block B. Each of these diagrams will illustrate the forces on the block and just on the block. Let me start with the A. So there must be gravity on block A of MAG. And since it's touching this surface here, I can say it has normal force from the surface. NA, I'm subscripting it because I'm anticipating a lot of normal forces. I want to make sure I don't get them confused. With these two forces, the potential direction of acceleration is in the wrong direction because I got the impression that block B will be accelerating down the ramp, which means block A should be accelerating up the ramp. Oh, I see. There's this string connected here, so there must be tension force on block A. And this tension force, which goes along the incline of the ramp, must be large enough so that when you add up all the forces, the direction of acceleration will be up the slope. Okay, that's block A. Let me do block B. So block B looks quite similar to block A in terms of forces that could be acting on it. So there must be gravity on block B and normal force from the surfaces touching and tension force that's again pulling it up the slope. But here we think it'll be accelerating downward. So so here the weight must be greater. So I think we can make that work. Oh, and we have friction force here. So while it's sliding down the slope, also accelerating down, the way you figure out the direction of friction is direction of friction will always be the direction that prevents the sliding between surfaces. So you first figure how will the surfaces slide against each other without friction, and friction is always introduced to make less of that happen. So here the friction force will be up the slope. Now, at this point, a common mistake to make is to think that this is the complete free body diagram and do the rest of the problem solving based on this diagram. And then you'll get some answer and it'll be slightly off. This is why step number one is the step that takes the most consideration, care, and time. And you really need to ask the question, did I draw all the forces? And I've been doing that. I've been introducing forces for gravity, and I've been introducing the contact forces for things that are touching the blocks. And here's one last check to do to make sure that you catch anything that you might have missed as you're doing that. And this is what I would like to call Newton's third law check. This is a check that you only need to do when you have multiple objects in your system, because you are checking for internal forces. So for each of the forces that we have drawn, we have to ask this question. Is this force being exerted by something that's internal to our system, the blocks that we are drawing, A and B, or is it external to the system? Usually, a lot of forces will be external. So both the gravitational forces are external. They come from Earth. Earth is not part of our system. And even the tension force is external. You can look at that as a force being exerted by the strings, which are external. Or even if you think of string as connecting the blocks to this pulley, well, the pulley is external as well. Okay, 4 forces down, 3 to go. Now we have these forces, the normal force on block B and the friction force. So again, you have to think about where the force comes from. It comes from this surface of contact. So it's the ramp that's exerting those contact forces, the normal force and the friction force. And since we are not considering ramp to be part of our system, they are both external forces. Which finally brings us to this point, the normal force on block A. It's coming from this surface of contact, so which object is exerting this force NA? You can see that it must be block B that's exerting that force. So Newton's third law says whenever block B exerts a force on block A by amount NA, then there must be a force on block B by block A. That's equal in magnitude and opposite in direction. And looking at my free body diagram for block B, I don't think I see that. I see this normal force, but that's an entirely different thing. And I don't see any other normal force. So I gotta draw that. Let me make some room. So what I need is a normal force that goes in the opposite direction of NA, drawn on free body diagram for A, and equal in magnitude. So, I guess I can use the same symbol, Na, to indicate that. And in fact, if you are doing the check of did I draw all the forces more thoroughly, you could have gotten this maybe without explicitly invoking Newton's third law. Because as you are considering block B, you could have noticed that block A is touching block B. So you could have figured there must be a normal force that's pushing down on block B. Now, the additional thing that Newton's third law does give you is that the magnitude of the normal force is something that we have already introduced in our free body diagram. So that's the complete step one. We have drawn all the forces and we have done this Newton's third law check to make sure that we didn't miss any forces of interaction. So now we are move on to step number two. That's the defining of the coordinate axis. We've already identified the direction of acceleration. So let me define my coordinate axis that way. So that actually means I'm going to have this direction be positive x for block A. And I'm actually going to flip the x direction around for block B because the acceleration for block B goes the other way. So let me label my axis as this downward direction is plus x. And let's make the y same as the block A. You don't have to define your axis this way, especially if you feel positive x going to the left looks weird. But if you don't define the axis this way, you have to be so much more careful in writing down the expression for acceleration. I think at this stage you will save a lot of trouble for yourself if you define your positive x-axis along the direction of acceleration, even when it's not the usual direction you would have chosen to be positive. Okay, that's step number two. Step number three is breaking down forces into components. And I see that for both of the free body diagrams, the one force I need to break down into components is the gravity. So let me draw the component, the x component, and the y component here. And similarly, let me move this B around again. Gravitational force on B has x and y components as well. Okay, here the given angle theta is this angle here. That's the theta of the incline. And I will leave the geometry up to you to prove that it's this angle here that has the same value as theta. I do highly recommend that you get practice now so that when you have to do this for other questions, as you surely will have to sometime in the semester, that you can do it correctly 100% of the time. Okay, I think that's enough. I will write down the magnitudes of these components as I'm writing down Newton's second law equations. These diagrams already look very crowded. For my step number 4, this is the final step in standard strategy. We'll write down Newton's second law equations. And you write down Newton's second law equation for every object in your system. So I'm going to be writing down net force on block A is equal to mass times acceleration of A, and net force on block B is equal to mass times acceleration of block B. And once again, these vector notations serve as a reminder that this one equation actually stands for all the related equations for different components. So let me just go through each line, writing down each of the 4 equations that I will be needing. Let me start from A in the x direction. So I have net force on A in x direction is okay. I'm looking at this free body diagram here for A. I have tension force in the x direction, and I have the x component of the gravitational force. So tension force is going in the positive direction, and I'm using the convention where I try to indicate the directions in my equation so that all the symbols will be a positive value. So it's a minus for the negative direction. The side I see here, it's opposite to the angle that we figured out is theta. So the x component here must be mag sine theta. That's equal to ma times acceleration. Okay, let's keep going. Net force for A again, but in the y direction. So net force on A in y direction is equal to, I have two forces again along the y direction. I have the normal force entirely in the y direction minus the y component of gravity, ma g cosine theta. I'm looking at how this side is adjacent to the angle theta. And in the y direction, the block doesn't accelerate. That's sort of the point of how you're choosing the coordinate axis. So this is equal to 0. All right, we are halfway done. I have to write down similar equations for block B. So it's going to be net force on block B in the x direction is equal to, oh, here I have to be careful. My positive axis was defined to be this direction here. So let me write down the x component of gravity first. That's mbg sine theta. And I have two other forces along the x direction, friction and tension. So that minus friction force and minus the tension force. That net force is equal to mass of B times acceleration. And it's the same acceleration, so we'll use the same symbol. We have one more equation, that is the net force on B in the y direction. That's equal to, I got more forces again. I have the normal force from the inclined plane. Let me write it down as positive NB. And I have the reaction force from the block A that's going in the negative y direction. So minus NA. And finally, we have the y component of the gravitational force. And again, given this angle theta, the y component is the adjacent side. So it's minus mbg cosine theta. And that's again equal to 0. Okay, let me leave the solution steps for your practice. Let me just verify that you have all the information necessary to solve for the given information. So this is a general rule in algebra. For you to be able to solve a system of equations, you need equal numbers of unknowns and equations. So we have 4 equations. So I'm hoping to find that we have 4 unknowns. Let's check. So we have tension force that we don't know. Mass, I'm going to assume that we know. G is a constant we know. Theta, I will assume that it's a given quantity because the question doesn't say we don't know that. But we won't know the acceleration because we are being asked. So we must not know it. Okay, 2 unknowns so far. I have the normal force on A, that's unknown, and no additional unknowns here. On equation 3, I have the mass, I'm gonna assume I know that. Friction force, I don't know, unless nowhere am I given the expression for friction force. Tension, I still don't know, I already counted it, so I won't count it a second time. Here, it might take a little bit of work showing that these two tension forces are the same. One statement in the question that does a lot of that work is this phrase, massless, frictionless pulley. If either of these are not right, then yeah, the tension could be different. But here, they are the same. Acceleration, I don't know, but we already counted that. Let's go into equation 4. And actually, before we do that, you can see that we will need the equation 4 because so far we've looked at 3 equations and we have 4 unknowns. So in equation 4, we have NB that we don't know. Okay, that's not looking good. NA, we don't know, but we already counted it, and the rest we already counted it. All right, so we have 4 equations and 5 unknowns. That does mean we are missing something, and this is where you have to maybe reread the question and make sure that you have reflected all the given information into your mathematical expressions here. And one piece of information that we did not use is the fact that the question gave coefficient of kinetic friction. And part A explicitly says assuming block B accelerates down. So we are in a kinetic situation that makes the formula for friction forces much simpler. And we'll have a separate video where we talk about friction with all the nuances. For the purpose of this question, all you have to know is that the friction force, that is the kinetic friction force, is given by the coefficient of kinetic friction times the normal force. That is the normal force between the surfaces where the friction is acting. So in this new equation, you can see that the friction force is something that we already counted as an unknown. So no new unknown there. We were given the coefficient of friction, so that's good. And the normal force here should be the NB, normal force between block B and the ramp. So now we do have 5 equations and 5 unknowns. So we, or you, should be able to solve this equation for 2 of those 5 unknowns, eliminating the other 3. And before we move on, it's in this equation where you can see that if we had missed out on this normal force, Na, the expression for Nb based on equation 4 will be different, and that'll result in discrepancy, which in this case is error, because not including this force would have been wrong. And there are other complications I can mention, but I think I'm already having you do enough on your own, so let me leave that there. For example 3, let me come back to example 1 and make it interesting. So this was our example 1, and this is how I propose to make it interesting. So as example 3, make it block on sliding inclined plane. So before I drew my inclined plane as some immovable thing, let's say it's its own block and its surfaces are so frictionless that it's able to slide freely on this horizontal table. Let me give it a mass begin. And here the one thing I can tell you is that the acceleration of this small block will no longer be a. So let's fully explore all the changes that we will now have to make. So let me copy this down the page so that I have more space. So the one change is we will have to draw an additional free body diagram because this ramp will be able to move as well. We have to consider how its motion will be affecting everything else. So we need a free body diagram of M, capital M. So there's gonna be gravity on the block, like with everything else. Now it's not accelerating downward, so there must be something that's opposing this gravitational force. Oh, and that'll be the normal force from this surface down here. Let me label that N2. Now this is where you have to consider carefully how will this sliding block now move. And I hope after giving it some thought, you will end with a conclusion that if it's going to accelerate in any direction, it will accelerate to the left. And this is one of the complications because this acceleration will not be the same as the other acceleration. So let me give it a different label. And considering this acceleration, I hope you see that this free body diagram is incomplete. It only has forces in the vertical directions. It doesn't have any forces in the horizontal direction. So where could we get those horizontal direction force? And I hope you find it after a while. If it helps, you can do the Newton's third law check. And in doing Newton's third law check, you should find that this normal force is now an internal force because it's a normal force exerted by the ramp of mass big M, and now this is part of our system. So we should find the reaction force pair on the ramp, and it's the 180 degrees from the direction of n on the small mass m. So let me just draw this auxiliary figure to correctly indicate the direction. Now, at this step, those of you who are working ahead might look at this situation and think, what has really changed for my free body diagram for the small mass m? Because it might look like all the forces that were there before are still here. Gravity is still there, normal force is still there, still no friction force. So you might think, doesn't that mean neither of these two equations change and the result that we derived before still hold? You might think that. And what you have to be careful is this. If this ramp is able to accelerate to the left, when you consider the acceleration of the small block m, it is still down the incline, as in the direction of acceleration of small block m will be parallel to this surface here. And I hope you find that that's not the case here. So what changes in this free body diagram are not the forces, and it's not as they are represented, but the direction of acceleration. Instead of being parallel to the incline, it will be in some direction, some component parallel to incline, and some component perpendicular to incline. So maybe something like this will be the direction of acceleration. And I will tell you, this is a difficult question. And I don't know if I would even recommend keeping this the same set of axes. This is one of those situations where the problem solving steps might be much cleaner if you just decided to use straight axes, x and y, and just to contend with there being x and y component of acceleration. It won't be pretty. And if you were to write down two additional equations that relate to the ramp of mass m, oh, and make sure to change these because with the change of coordinate axis, how your force components are expressed will be different. And after finishing writing down the set of equations for the ramp, I think at least the axis for the ramp is easy. I think I can let this be the positive x direction so that the ramp will be accelerating in the positive x direction and it's not going to be accelerating in the vertical direction. So I'll be able to call this mass times A2. That's the label I started using. And net force in the y direction results in 0 acceleration. Now, what I was saying was, after you finish writing down all these additional equations, I think you will find that you have more unknowns than equations. It goes to the fact that deciding to handle two components of acceleration separately resulted in basically this additional unknown. So you have to write down an additional equation, maybe something relating to how these two things are to remain in contact. Then there is some relationship between this acceleration as a vector quantity and this acceleration. I guess the idea here is that the acceleration vector plus the A2 vector that results in some vector quantity, and this should still be at angle theta. That is, I said how this acceleration won't be along the slope of the incline, but if you correct for the fact that the ramp is moving, then the path that this mass is going with that correction should be along that incline. Then I think this is not actually plus or but minus, looking at the figures. So you have to figure out a way to mathematically express that. That might be something like, let me try to wing something here. I think I can do this. Tangent of theta is equal to the y component over the x component of this resultant thing. So it would be something like a y over ay as labeled here, and I would need a x plus A2, both as positive quantities. So in graphical representation, something like this. The downward acceleration of AY and the rightward acceleration of AX plus the correction for the ramp moving A2. This triangle should be similar to the triangle of the ramp, and this should be angle theta. So again, this is a difficult situation to work out, and I won't ever give you a question like this to do even on homework because again, it's difficult. But you can see how the standard strategy lets you explore all these complications that arises from making this change. And for those of you who are inclined to tackle it, I do believe you have all the tools that you need to work through this system of 5 equations and get an answer. And this is possible using the systematic problem solving approach like the standard strategy. If you were to try to work through this intuitively without a structured system, it's quite difficult to know what the next thing to do is. So let me end the examples here. As I said in the other video, you'll see a lot more examples of application of the standard strategy, about 2 dozen times just on me working through your homework questions. So if these 3 examples left you with some questions, watch out for those other videos working through your homework questions and see if you can follow. Like we do all physics problem solving, the Newton's law problem solving, the only way to get good at solving problems like these is through practice. So after watching these lecture videos and reading through some of the portable TA problems and solutions, I strongly recommend that you try working out the problems yourself without referring to any of these explanations that you might have looked at first. As you try to do these questions on your own, you will be able to figure out what you quite didn't get the first time around. And you can go back and look at the lecture videos or the portable TA again, find what you saw the first time but didn't quite understand, and try the problem again. I strongly recommend this regime of practice. So, drawing free body diagram itself will take some practice. And once you do that, then you have these steps laid out. Step number 2, step number 3. And by the time you get to step number 4, really all you have to do is read off information that's already in the diagram. So let me give you a bit of a comparison between how we give you these 4 steps and how the textbook and the portable TA lays it out. Let me bring over the textbook from my other window. So this is the set of steps that are in your textbook. So your textbook doesn't give you really a single reference for Newton's law strategy, but let me just link up those things that are both in the textbook and in what we give you, so that it doesn't look like, so that you can see the connections. So in your textbook, what we lay out as a standard strategy is broken out in 2 sections. One is in chapter 5.7, drawing free body diagrams. And in chapter 5, there are some questions where you could use detailed force problem solving strategy, but much of that has been reserved for chapter 6, applications of Newton's laws. So in that organization of the textbook, the whole layout of this strategy kind of gets broken up into 2 pieces, which I think is a little bit unfortunate. So the first part is in section 5.7, and it's in problem solving strategy, constructing or drawing free body diagrams. So this is what your textbook says, and let me just draw the comparison. So in your textbook, it tells you draw the object under consideration. It says it does not have to be artistic, and so we take it to an extreme, and it does say if you are treating the object as a particle, represent the object as a point, and that's what you are seeing us do so far in this class. As in, we are using these dots to represent the entire object, regardless of its size and shape. And later on in the semester, especially after we've introduced the rotation, after exam 2, we will start to draw more extended bodies as our object when we are drawing free body diagram. But for now, most of the time, you'll be drawing a single dot, or I'll be drawing a single dot. And step number 2 here says, include all the forces that act on the object, representing these forces as vectors. So those are the arrows that I was drawing on the free body diagram. And these 2 steps that are outlined here correspond to our step number 1, drawing free body diagram. And it's kind of difficult to describe all the things that should be going on in writing. So that's why you have a few videos, including the videos from last week that illustrate the process for drawing free body diagram. And what we give you as step number 2, it might look like in your textbook, there's no step number 2. This is something that we are kind of pulling out from a step that is given in the textbook. So the textbook says, convert the free body diagram into a more detailed diagram showing the X and Y components, which corresponds to our step number 3, break down forces into their components. Now, here's something that the textbook presumes that you have. X and Y components. You can't really talk about components until you have the axis. Now, if you're always dealing with a straight axis, then it's obvious what the X and Y directions are. But very commonly, especially in this class, you will have situations where it's more convenient to use axes that are tilted. That's why that's the reason we break out step number 2, so that we are encouraging you to give some thought to how you choose your X and Y axis. And really what matters here is, as Ben points out in his video, is the direction of the acceleration. And this advice is looking forward to step number 4, where you are writing down Newton's second law equation. And this vector equation really represents multiple equations, or one for the X component, one for the Y component. And we kind of recognize or realize that our equations are going to look simpler if we can set one of these equal to 0. And we do that in step number 2 by choosing our coordinate axis very carefully. You don't have to, I guess. You can always choose straight axis, and it's still doable, but in many cases, you can be creating more work for yourself that you didn't have to create. So that's step number 3. And I guess what they are telling you in this step number 4, if there are 2 or more objects, draw separate free body diagram for each object. That feels like that's something you should have right at the beginning when you are actually drawing the free body diagram. But anyways, so we just put them in the right order so that you start thinking about drawing the free body diagram for each object from the very first step, instead of checking to see if you did it wrong after you've done it. So the one step that your textbook leaves out is the step number 4. And that's a kind of a consequence of how the textbook breaks out these problem-solving strategy into two sections, one in chapter 5 and one in chapter 6. So in chapter 6, they give you what they call problem-solving strategy, applying Newton's laws of motion. And some of the steps that they are laying out here is a bit duplicative, because these first three steps here, this is a drawing free body diagram, as they already covered in section 5.7. So really the only new thing that they are introducing here is what they are saying: apply Newton's second law to solve the problem. And our application of Newton's second law is writing down this equation. And the idea is that if you have followed these steps, which is, I guess, kind of, well, it doesn't match number for number, but it is our steps 1 through 3. If you have done that, then all the information you need to write down Newton's second law for equation for each object, it should already all be in the diagram. All you are doing is this step now is simply reading off the information. So that's how it matches up with textbook strategy. Now, there's something we kind of omit in standard strategy. In particular, so in your textbook, it says, if necessary, apply appropriate kinematic equations from the chapter on motion along a straight line. And it says something about check the solution to see whether it's reasonable. And all that's good. I don't include them as part of standard strategy, because I guess what I want to impress on you is that this doesn't actually solve the problem for you. It sets you up to solve the problem. Because once you have written down Newton's second law equations, then what you have left is a system of equations on which you can do the algebra to try to solve for the unknowns. And sometimes, depending on the problem, you might have to bring in additional information, like the kinematics equations, to have enough number of equations for the number of unknowns you have, and solve that. So really, there's a step number 5, which is actually solving the problem. But once you get to step number 4 and you have system of equations, then most of you know how to go from there and solve your system of equations to actually get a result. And checking to see whether solution is reasonable, that's a habit you should be building, and we'll be illustrating that plenty of times throughout this semester. Okay, so that's it, how it matches up with the textbook. Let me show you the example from the Portable TA to show you how it matches up with what you will see in Portable TA. So this is question A6. And it actually deals with a situation that's quite a bit similar to the question that you are dealing with in your lab, with a bit of a special modification in that the theta is equal to 0 for the situation in the lab. But otherwise, it's dealing with the 2 blocks connected by string, so it's quite similar. So, so as it says, this is a classic multi-block problem. And in the answer, Andrew Elby introduces what he calls multi-block strategy. This is what he introduces. He says, draw a free body diagram for each mass individually. So what it calls step number 1 here, that matches up with our step number 1, draw a free body diagram individually for each object. And then if you just read step number 2, it kind of looks like he skipped right up to step number 4 here. And our purpose for providing steps number 2 and 3 is to give you the guidance how to go from a free body diagram to writing the Newton's second law equation. And as you read through what Andrew Elby wrote in the Portable TA, you can see how they do match up. So I feel like ours is a slightly polished version of the strategy that he describes in the Portable TA. So as you might have noticed when I drew free body diagram here, after you're done drawing free body diagram, if you're immediately trying to write down Newton's second law, especially in the component form, you're skipping a bit of a step here. What's your x direction? What's your y direction? And in his instructions too, Andrew says to I guess in this strategy, he's giving you something that's a bit of a one-dimensional thing, because he wants you to write Newton's second law along the direction of motion. So he's imagining defining one axis, x-axis, along the direction of motion of the mass. So we do that explicitly in step number 2 by identifying the direction of acceleration and using that to choose a coordinate system. And the coordinate system is chosen for each object separately, as you see him do here with these objects. So the mass on the ramp is accelerating this way, possibly. So that's the x-axis. The hanging mass is accelerating down, possibly. So that's chosen as the x-axis. And in order to write down this Newton's second law along those directions, you need to, so when forces are either along that direction or perpendicular to it, right? You have no additional work to do. But sometimes you will have some forces that are not in one or the other direction, but kind of diagonally. It's a combination of both the directions. That's where you do need to break it down into components so that you can see which direction of forces is perpendicular to the direction of motion and which direction is parallel to the direction of motion. So, so in step number 2, he says quite a bit here, and that's broken down explicitly in our steps number 2 and 3. And just one additional thing, he calls it a multi-block strategy. But if you have a single block, it's not multi-block, but you can use the exact same strategy. I guess the difference might be that a lot of you might feel like with many single object situations that you have enough intuition to get to the answer without going through this complicated strategy. And for many of you, that might be true. And if you are saying, all right, I just want to skip right to the answer, and there's nothing wrong with that. But what I want to caution you with is there are some questions where your intuition will fail you. You won't know quite what the next step to do is. And that's where this standard strategy really shines, because this is the detailed, systematic set of steps where you are able to follow from one step to next, and once again, each bite-sized chunk so that you can chew each piece without too much difficulty. So let me show you some examples of questions where I'm hoping if you are trying to approach that intuitively, it'll stump you. But if you break it out the way we lay it out for you, then you'll be able to work through the setup.